So this simulation, it is an overview of waves, and there's several things that I want to talk about to show you. First of all, of course, you have this little wrench and this string. It looks like, how many of these lines are there? How many of these little dots? 1, 2, 3, 4, 5. Yeah, there's 5 dots in the middle here, and it's clamped on this end. Of course, we can change the clamping if we want. But the first thing that you, of course, do is play with the wrench and wiggle the wrench up and down. Woo! Yeah, you just do this and realize, okay, that's kind of neat. Nice simulation. So spend some time doing that and how you feel about that. But then we want to move on to some more more structured topics. And so that was the manual. Let's move to the pulse. There are several things I want to mention about the pulse. So down here on the so-called dashboard, you have damping, and I'm going to have 0 damping here. We got the tension in the string, which is set to high. Amplitude, right, in centimeters. If you take a ruler, there certainly is a ruler on this options. Make these rulers, then you can show that, and we'll do those in a minute, you can show that the amplitude in that ruler actually of this pulse does measure like 0.75 centimeters or something. And then the pulse width, look at the pulse width, that is set to seconds. So it's the time at which this oscillating object goes up and then goes down. So it takes 0.75 seconds for a single pulse. So we're just kind of wiggling it up, and then we're going back to where we started. So let's run that. Over here, boom. And so off the bat, we automatically see some interesting features about this, this triangular pulse. So evidently, when a wave, so this is a wave. I mean, that's really the first part. Oh, we had 2 pulses. Didn't mean to do that. Certainly that's interesting. And now, of course, what are you going to do? You're just going to add a bunch of pulses, right? See what happens and see how the jumble. So this is a jumbled mess, but it is like just 3 or 4 of those pulses added together. Certainly interesting, but let's reset the thing. Okay, if I reset, it goes back to the manual. So I need to just switch back to the pulse. So let's go back to this pulse here. So let's just do 1. Again, scrubbing off the damping. There you go. So I meant to press the pause button. There's a pause button right here, and you can pause it. And this is like a frame by frame type button that you can go. It is really the next step in the calculation. I mean, it's the next step in the calculation that the program controls. And so if I do that, you see that the clamp on the right-hand side fixes the string to be at value 0. What do we mean by value 0? Well, this is a pulse of energy that's traveling along a medium, and that's how we want to think about it generally. We have a amplitude, we have a displacement from equilibrium of all of these points on a string. So we're describing this wave, okay, we're describing this pulse as a function of the length of the string. And the value of the function on the left side is obviously 0, and the value of the function right here is increasing to a maximum and then decreasing back to 0, and then it ends up being 0. So that's how you describe a wave. You describe it as a displacement of something from equilibrium. In this case, it's literally position of the string from equilibrium. And this boundary on the right-hand side requires that the value of this displacement on the left and the right-hand side both be 0. And so when we require that, we'll get this effect where if the string is required to be at 0, what's going to happen when this wave comes to it? And we've already seen it, but of course what happens is that the only thing that can happen is that the wave has to go under to kind of cancel itself out on that right-hand side. And so we can shift forward and you can start to see that the wave has to go under itself. So the wave has to go under itself to pass through it. And so eventually, what you see is that there's part of the wave that's still up, but now there's part of the wave starting to reflect down. And sure enough, at this point, you have exactly half of the triangle. This is the part in the wave where the top part of the triangle has hit the edge. And so what you see is that there's I can annotate this, might be kind of interesting. That means, excuse me, that I need to switch pins real quick. Now this means that the left half of the triangle, oh, sorry, okay, there we go. The left half of the triangle is still moving this way, whereas the right part of the triangle is now moving that way, and they cancel out. And so sure enough, what will happen in time is that this part will move forward, and then this part will move outwards until all of it has reflected. And so if we see that in time, sorry, sometimes I just tap on the touchpad and I accidentally move the bar. So now we see the left hand, it's starting to emerge on the lower side. So now more and more of the wave is appearing on the bottom, but this is still part of the wave that's on the top, and then eventually now it's all at the top. And if you continue that, obviously that'll go on the other side too. So when waves reflect at a boundary, depending on the type of boundary, they may reflect downward, or they might actually reflect upward. Let me pause it again. I'll wait for it to finish. Okay, now let's switch the boundary up here to the loose end. Now, the loose end, these are what are called boundary conditions, and boundary conditions are everywhere when we're talking about waves, because you always have to specify. So if this disturbance is moving through a medium, you always have to ask yourself what's going to happen to the disturbance at the boundary. For instance, right, if you look inside, if you're inside your home and you look outside the window, the light from your lamp, there's part of it that's passed through the window, but part of it that is bounced back. And so, that would be an example of the light wave interacting with the glass boundary. You have to consider what happens to that wave as it hits that boundary. And the same thing here. We're requiring that none of the wave passes through the other side, but with this movable boundary on the far right side, we're actually going to require that the wave is flat on the very right edge of the boundary. So if it's flat, then we can move forward. Let's do it in slow-mo. Let's do it frame by frame first, and then we'll see what happens. Okay. So moving frame by frame, moving forward. But once it gets there, now the fact that the slope of the wave has to be 0 enforces that it starts to bounce upward. Okay, so this slope on the edge of this loose end is required to be 0. So what do I mean by slope? I mean by the derivative of the actual displacement of the wave. It has to be 0 on the edge. So it has to be a flat line. And of course, what you see, the more steps you take, it stays flat. And then it keeps going. And so evidently this wave kind of adds together on the left edge and bounces back. And so we can play it now, and I'll show you the full effect. So under, and now bouncing back, over, bounce back, under, bounce back, over, bounce back. So that is what happens when a pulse hits a specific boundary. This simulation certainly does not account for this, but you can also consider situations where this is not a, this is because it's like a wall. This is like a wall to the, and incidentally, so also is this. This is like a wave that's trapped in a wall. And if the wave is free to move past the wall, then that will affect how it responds. Let's see, let me erase that. For instance, let me show you something like this. If you have a very light string, well, actually, this is where you can be kind of creative with zoom. So if I have a string that is very light, and then it is connected and like kind of tied together with the string that is very thick, right? Then what will happen is actually kind of interesting. So if I send in the pulse, so if I send in a pulse in this direction, oops, this is really worth considering. So let me go back and switch between fonts. So if the wave on the thin part is moving towards the wave with the thick part, what we'll actually observe is part of the wave will reflect back downward, okay? And the other part of it will transmit through upward. So if a thin wave, and this, yeah, this is a interesting question. So this is a different type of boundary because the wave is allowed to pass through. Whether in this simulation, the wave is just stuck in between the walls. But if it's allowed to pass through, then you'll have a smaller wave, and that's actually moving at a lower speed. It's actually it's rebounding on the same speed. Now, of course, if you turn the problem around and send in a wave on the thick end, I think rather than trying to navigate it, if you send it from the thick end to the thin end, it'll actually bounce back on with the same height, but the transmitted wave will actually zoom off. And so when you're dealing with boundaries, evidently for this waves on strings, the density of the string, if it's different at two different spots, that'll affect how the wave bounces or transmits through. And you can use some, intuition to think about it. I mean, if you have let's say you drop a rock in a pond, and then, next to the rock is because some muddy water. Well, the muddy water has more mass in it, and so it's not going to go as high, and it's going to move more slowly. And so you can more or less say that the thicker the material is, the more dense the material is, the slower a wave will move through it. And that's pretty general. Yeah, so this is the wave pulse. But of course, what happens if the boundary is free? If there's no boundary, well, then we're just left to the wave to just kind of continue out of our domain, and it just goes away. It bounces and then just leaves, and then there's nothing left. This is a good way to model how a particle moves in without any forces, how a little wave moves without any forces. So what we're interested now is the sinusoidal wave. So I'm going to switch from a pulse to up here to oscillate. And sure enough, we see our first example of a traveling sinusoidal wave. So this sinusoidal wave is a function of the entire length of the string. So it's got a component x, but it's also changing in time, right? I mean, let's see, if we start off with the string like this, then I'm choosing pin. I'm choosing another pin. Just for fun, I'm going to kind of trace this so we can see what it looks like a certain instant in time later. So this is the value of the wave at this time, right? And so this is the dx at a certain time, at time t equals t sub 0, for instance. It's a sine wave, and so it is, it's going to be the amplitude times either the sine or the cosine of 2 pi over lambda times x plus a phase difference, plus a phase factor. And so the wavelength of this string is the typical thing you would expect for wavelength, which is if it's at 0, it has to go all the way up and then all the way down and then back. So that is the wavelength of the string, or the wave, not the string, the wavelength of the sinusoidal wave, right? Also, sometimes we do the peak to peak width or the valley to valley width. That's the same thing, okay, for the wavelength. But yeah, this is also an example where it's changing in time. And so if we graph the entirety of the wave at a single instant in time, we get the whole shape. What is also we do sometimes is, and that's called a snapshot graph. But if we then consider a single spot, let's consider let's consider a single spot. We'll do this spot right here. Actually, no, let's consider, it doesn't matter, I guess, but yeah, let's consider this spot right here, okay? And what would be the graph of the displacement versus time of this thing? Well, now we can do some time steps and show, okay, turn off the pen and come back here, do some time steps. And we can show that in this case, what's going to happen to the position of the single point in time. After all that to say, what's that point going to do? It's going up, right? And so then it's going down, looking at really the imaginary position of the single point, and then it's going down further, and then it's going up. And so this point right here oscillates up and then oscillates down. And then, so that would be a similar sinusoidal shape on the displacement versus time graph, but that'd be displacement versus time for a specific x. And so that's called a history graph, when you are able to look at a single location in the medium and get a value of the displacement for all times. What's the speed of this wave? That's probably another question worth asking. How do we measure the speed of the wave? Well, I mean, if you have a rock in a pond, you can certainly take a recording, as maybe you've done in the physics labs this semester. You've been taking them. You can certainly take a recording with a stopwatch and measure, you know, the distance that the ripple travels, the single ripple travels in time, and that's certainly a great way to find the speed. But how do you find the speed of a sinusoidal wave? Well, you just have to look at the distance that a peak would travel. And so if I move this a little bit forward, it doesn't really matter, but let's take a look at, yeah. So this spot right, we can do a couple more time steps. Yeah, so now this bright dot right here is right in the middle. What's the wavelength of this thing? Well, the ruler is pretty straightforward to measure that. This is obviously very basic, but sometimes these basic things are fun. So if I line it up about as close as I can here, a little bit more to the right. I mean, there's going to be some error in my measurement, as silly as that sounds. No, if that measurement is 0, then what is the wavelength? Peak to peak width is going to give us a wavelength of about, I don't know. If this is in centimeters, what are these? 1, 2, 3, 4. Oh, these are 0.2. So the wavelength, you could clearly do an uncertainty calculation. The wavelength, I would say, you know, is 4.2 plus or minus 0.1. or so centimeters. Okay, now how long does it take this part of the wave to travel a distance equal to the wavelength? So what I'm going to do is I'm going to take this part, the energy at this spot, and see how long it takes to go from the starting point to the initial point. And that's actually how we can define our speed. So the timer here, and it's really easy when you can just freeze frame it. So let's see what happens. And let's try and kind of experimentally find a location. Sure enough, I got zoom, so I can annotate. And let's have this be the finish line, have this be the starting line. I guess these are actually displacement vectors. So it is technically a vector. Let's see what we find. So clocks started technically, but we're paused, and so we can, we can start moving it. So go. And the clock is actually running. I get it? Where are we at? Very nearly that, maybe one more tick. That's about close. So the energy that was at this spot has now moved to this spot in a distance of 4 centimeters in a time equal to what? 0.66. 0.66. I wonder how much each tick is actually. Each tick was about 0.02 seconds. Okay. So the speed of the wave is then calculated in the straightforward distance over time way, but it's the distance that, what was the distance that we traveled? Well, this energy traveled a complete wavelength. So the distance traveled was the wavelength of the wave. What was the time? Well, you would say the time would be 0.66, but we can go further than that. If you graph the displacement as a function of time for this spot, d as a function of t, well, then the peak to peak width, if you remember from chapter 15, is defined as the period. This is a graph of displacement as a function of time for this spot on the wave. So this is a snapshot graph. Of course, we have the history graph here. So we're actually calculating the speed of the wave as the energy at this spot traveling a distance equal to its wavelength in a time equal to its period. And sure enough, for these values that were given, the period we measured 0.66. We had 4 centimeters. So 4, V equals 4 centimeters divided by 0.66. 66 is obviously 2/3. And so dividing by 2/3 multiplied by 3/2, we get around, plus or minus, with uncertainty, about 6 centimeters per second. 6 centimeters per second is the speed of this wave. Okay. Now, here's the part that tends to throw people off. What if we change the frequency? So that was a frequency that was, it was medium, 1.5 hertz, which, by the way, multiply 4 centimeters, the wavelength, by 1.5 hertz, you also get 6 centimeters per second. And so the equation that is most often remembered for the speed of a wave, at least in the introductory setting, would be that the speed of the wave V equals, I'll even write that on the side, keep it there, V equals lambda times F. And that's a very common equation for the speed of a wave. What I want to show you, though, is that as the frequency goes down, let's see what happens. I'm not going to clear, I'm just going to get rid of the annotate bar so I can go on here. What's going to happen if I double the frequency? Is the thing moving faster or not? Well, let's play it and find out. I'll get rid of this. I'll get rid of these tools so we can just look at it. So we double the frequency. Is it moving faster? Well, you know how to take a measurement. let's do the same sort of measurement that we just did. We could certainly multiply the frequency by the wavelength, but now we have to measure the wavelength at the very least, and the timer is always fun. Oh, the timer was going, okay. So what's the new wavelength here? Doesn't matter, but okay. We'll just start right here, roughly that 0 spot. So the wavelength is close to 2 centimeters. And so let's take the time that it takes the energy at this location to travel to this location, which would be, again, a peak-to-peak width. So starting that thing, I'm not going to do all the other annotations. About right here. So in that time, the energy that was at this location is now at this location. What was that time? 0.32, which is about 1/3, right? And so you take 2 centimeters, the wavelength, divided by the time it took the energy to travel those 2 centimeters, which was a period of 0.32, you get the same answer. And sure enough, you could have just, if you knew that the wavelength was 2 centimeters, you could have just worked in the frequency domain by just multiplying the 2 centimeters by the applied frequency. And so even though, as I kind of get rid of all this other stuff, even though it's certainly waving a lot faster, the whole wave is moving at the same speed. Okay, this thing, the maximum speed of this thing is definitely faster, right? If I lower the frequency, you certainly see that the maximum speed of the maximum speed of a single point is fast. It's faster. That means the point has more energy. So if we lower it, right, this point is on the average moving slower, right? The stuff from oscillation is still true. The maximum speed is still at the center. And so here's one thing that is different. If I pause it, the maximum speed for this short wavelength, or sorry, for this long wavelength, okay, it's pretty small. So Vmax, this is Vmax up and down, the vector velocity of the point for a small wavelength. Now, if I go to the long wave, if I go to the high frequency stuff, increase the wavelength, increase the frequency to its maximum. The thing that's moving faster is the motion on each of these points. And so now if I look at the max speed at this point, it is much bigger. Right? The max speed, well, you have to, max speed at the center here is much bigger. So Vmax for a high frequency is much bigger than Vmax for low frequency. So there's 2 speeds here. There's the speed of the wave, V of the wave, and then there's the oscillation of a single point. The oscillation of a single point is faster, but the whole wave stays constant. The whole wave travels at the same speed. That's why this thing looks to be moving faster, because it, and I will delete it all now. That way it appears to be moving faster, but it's moving faster in the transverse direction. It's moving, the disturbance is traveling at the same speed in the direction of propagation. And we just showed that with the calculation. You could certainly use some sort of, calculations from oscillation to figure out the maximum speed of a wave. I mean, the period, I'm trying to figure out the easiest way to do it. But the fact that they're oscillating more rapidly at a higher frequency means they have more energy. So a higher frequency wave will correspond to more energy traveling at the same speed. And a lower frequency wave corresponds to less energy traveling at the same speed. So that's what's different, is the amount of energy that's transported from the change in frequency, which you control that. You control the change in the frequency. What the medium dictates is the speed of the wave. That's set by the medium. The wavelength is the response of that medium to the frequency. So in looking at that equation again, the equation of speed equals lambda times f, right? The frequency is from the source. The velocity or the speed is a property of the medium, we call it the medium. And so the lambda is kind of the effect or the response. Okay, so these, when you look at this equation, there's not much causality that's implied in it. That's what the causality is. Okay, the frequency is the source. You control that. The environment or the external applied forces controls the frequency. The velocity or the speed in the speed of the wave in the medium depends on the medium, and the wavelength is the response. So the wavelength, when you change mediums, the wavelength will go down. Like if you go back to that example of the thin string and then the connected to the thick string, okay, what'll happen is if you send in a wave like this, it will, the frequency will be the same. So the frequency of this, maybe F1, so this is medium 1, medium 2, the frequency will be the same, but the speed, since the object is bigger, the speed V2 will be less than V1 because the string is bigger. More on that in a minute. And so if these both equal lambda 2, so if you have that lambda 2 F2 is less than lambda 1 F1, and the frequencies are equal, then the wavelength is smaller. And so you'll see if this is the wavelength of the string in the thin string, then it's going to be something like this. That's how the wave will travel through the medium when it goes from a thicker string to a thinner string to a thicker string. So, because the frequency of this wave is the same as the frequency of this wave. That's the thing that stays the same. This is moving very quickly. This one's moving very slowly. And so the decrease in the velocity accounts for the decrease in the wavelength. And also the amplitude. I mean, the amplitude goes down in some sense as well. That's not something that I want to talk about here, though. Because there's part of the energy that's being transported. Okay, so this is a very qualitative overall picture of waves. Certainly, there's more to say about this simulation. So we'll continue then talking about this on the PowerPoints, though. So that with that overview of the simulation, the kind of broad introduction, just mentioning a few key points that are important for the vocabulary. So the first type of wave, so waves, all sorts of different waves that you can think of, obviously. You can think of, you see these waves on a string, there's waves like on a slinky, there's water waves, there's sound waves, there's light waves, there's earthquake type seismic waves. Those are some of the big ones that people can think of off the top of their head. There's a whole lot more in physics. I mean, there's even you can even describe the propagation of energy in a solid as a traveling wave. It's anything that transports energy through a medium. That's the general definition. And this is a transverse wave, right? If you flick the string, the transverse wave means that the displacement is perpendicular to the direction of motion. This pulse is moving probably to the right, okay? But the string, the points on the string or rope are moving up and down. That's a transverse wave. Examples of transverse waves, obviously waves on strings, obviously water waves, because you see the rock, you see the puddles ripple up and down as they move outwards. Light also happens to be a transverse wave, although you can't really see the thing that's waving in light. And in fact, there's a whole course on that related to that. That's called Physics 2. But here's a transverse wave, or sorry, here's a longitudinal wave. Longitudinal wave is one that the compression occurs in the direction of the displacement. So imagine like a snake that's perfectly stretched out, and how's it going to move? It has to kind of compress on the back end of its tail, and then that compression causes the next part to compress, which causes the last part to extend. So this compression, extension follows over the entirety of the snake's body, and you're able to propel yourself forward. Well, we certainly have this picture here where you have the, you have the string, somewhat like a slinky now. This part here is a compression. And so these 2 points get closer together as all the other ones are staying the same distance apart. And this this compression moves along the direction of the object. And so that's a resulting longitudinal wave. So longitudinal wave is when the displacement is along the direction of propagation. Here's a nice way to summarize them. For a compression, so the velocity is parallel to the displacement. I have to change my font quickly, or my color. For a longitudinal wave, you actually have that the displacement across the velocity of the wave is 0, right? Because these two are parallel, d and v. Compare that to a transverse wave. I'll just kind of write it here somewhere, right? If this wave is moving, the transverse wave, you got d up, v to the right. So for a transverse wave, you have d dot v is 0. So that'd be d dot v is 0. So one of the waves has a vanishing dot product. The other wave has a vanishing cross product. What do those magnitudes of those dot products and cross products mean? Not sure if that is clear, but it's interesting to classify these things in terms of their vanishing dot products and cross products. I mean, obviously, cross product, just a vanishing cross product just means that the vectors are parallel or anti-parallel. And a vanishing dot product means that the vectors are perpendicular. That's it. So, but that's something that advanced theories in later courses, they characterize different vectors. Anyway, so you got longitudinal and you got transverse waves. And of course, now the last sort of topic then from this original thing is the actual speed of a wave on a string. We didn't show this in the simulation, but the speed of a wave is proportional to the square root of the tension. So the tighter the string, the faster the pulse will move, and divided by the linear mass density, right? The linear mass density, Greek letter mu, the same symbol for friction, is just the total mass divided by the total length. This is the typical thing you would expect. And for most of these strings, you would say that reduced mass is constant. So that is the starting point of a speed on the wave. And if we take a look at this quick check question real quick, we see 2 different waves, 2 different pulses on the same string. How do their speeds compare? Okay, the speed of the wave is equal. Okay, the maximum speed, okay, and that's what this question is asking. How do the speeds of these pulses compare? Okay, but as the tangent or the upward velocity of each point at the center, that is different. Okay, and the fact that these 2 vectors are different mean that this one has more energy. E2 is greater than E1. As we're going to find out, the energy of one of these waves is proportional to the amplitude, the amplitude of the vector. Technically is the square, actually, of the, yeah, it's a square of the wave. So that's a brief introduction to waves. There's a nice simulation. What we'll continue to do in the next classes is what we'll talk about how waves add together, kind of an overview of different types of waves. We'll focus on sound waves, talk about decibels, maybe the Doppler effect, but just kind of pick and choose different topics from these chapters. And for tests, I'll certainly be clear about what I want for the test. So I'll be specific in the study guide of what I want on the test. But for now, that's it for this lecture.